So I'm talking about surface and groundwater. And I want to start this off with the regional satellite image. This is from the Landsat program. And one of the points I like to make, and I don't like to put boundaries on these things because it's one big desert. It's one big sky the rain falls out of. It doesn't matter which side of the river. It's all part of the same system. And if we can, I'll try to point out a few features. You can see where we are. That's the star. And then Van Horn is up here. Big Bend National Park is right here. The river, Amistad Reservoir is over there. The Pecos, the Devils, the Rio Conchos comes in over here by Ojinaga. So for reference, this is what I'm talking about today, surface and groundwater over this whole area. Okay, so it's water. It all starts with precipitation. This is a map of 30-year averages for the country. And a couple of things we can point out with this is the 100th meridian, John Wesley Powell, or the book by Wallace Stegner. That's this line right here. So we're sort of part of the west side of the 100th meridian, the dry side. So we get an average, if you can look at the legend here, somewhere between, we heard today, this morning 10 to 14, just a little bit more than that. The next slide will show that. This is from a report that we did in 2004. And basically the conclusion from this is that these precipitation sites that are on the graph show the relationship between precipitation and elevation. So in Boquillas, the number's about 10 inches per year, low elevation, and at Mount Rock, it's almost 20. So we could just conclude somewhere, depending on your elevation, that the precipitation is 10 to 20 inches. So I'm going to start off talking about surface water. And we really look at surface water resources effectively by looking at topography and drainage basins. So this boundary is the Rio Grande / Rio Bravo, if you're in Mexico, / Rio Conchos, which is a major tributary that is located here. The confluence of the Conchos and the Rio Grande is at Presidio and Ojinaga. The headwaters of the Rio Grande are up in Colorado, and of course it flows to the Gulf of Mexico. And I'm going to use a term that I refer to as HUCs. They're hydrologic unit codes. You see it says the HUC 13. The Rio Grande Basin is given the 2-digit value of 13. And secondly, the HUC numbers that are labeled here is 4 and 8. The farther up you go in number, the smaller the drainage subdivision is. And what this one is intended to point out is that there are subdivisions or subbasins of the Rio Grande that include the Pecos, which we're actually in Alpine. Alpine Creek flows northeast. Confluence of it with the Pecos is up by Cayenosa, and then it turns and heads toward the Rio Grande. And just 10 miles south of Alpine is the Rio Grande Amistad component of this. That's a HUC 4 designation. And then there's a closed basin up by Van Horn. And then the Devils and the Pecos rivers are on the east. So we can model and predict water resources based upon surface topography, which is what, rain falls and then flows downhill. The light's flashing. So here's what we know, some of what we know. There's a really important flow history that is in records collected by either the International Boundary and Water Commission, that's the IBWC, or the USGS, United States Geological Survey. And what they do is they maintain stream gauges for various reasons. The IBWC does it for treaty delivery obligations, 1944 treaty with Mexico, among other things. And then the USGS and other entities do it on rivers that include the Rio Grande, the Pecos, the Devils, for compact delivery obligations, et cetera. There are a lot of reasons to do this. So the upper right picture is a picture of the stream gauge on the lower Pecos, a very deep canyon with a cableway that you go across to drop instruments down into the water if it's high enough. The lower right one is the mighty Rio Grande above Presidio, where you just basically can just measure the flow by wading across at this level. But if you notice, there's a cable up there. So when the water's higher, you can suspend the instruments from that cable. So that's how it works. They go out periodically and either measure directly or drop instruments to measure the cross-section and the velocity and determine the flow per a day. And that record is downloadable from USGS or IBWC, and it goes back in some cases to before 1900. So we have this really interesting history of stream flow thanks to the IBWC and the USGS. The lower left map shows a subset of the gauges that we used for a report that I'll refer to in a minute. And you may be able to see a couple of dots on there. They're scattered across the Rio Grande, on the Devils, and on the Pecos. So these slides I'm going to show, the next four, are courtesy of Jack Smith at Utah State. He's working with us in Big Bend on the Rio Grande. And he really put together an interesting story by looking at the history of these gauges. So this map, the width of the line is proportional to the flow in that reach. And this is the prior to 1915 subset. 1915 is when Bureau of Rec started putting in dams like Elephant Butte. Equivalent agencies in Mexico did the same on the Rio Grande. So this is as close as we can get to pre-development, even though it's not pre-development, because there were already manipulations being done on it. So, but basically, you can see the story is the Rio Grande starts in Colorado, and once it flows into Texas, it was, even before appropriated water, it was already a losing reach. So that means that part that's right here is not as wide as there. And then the Conchos comes in, and it's a really big wide, 74 cubic meters per second, kind of average flows, which is really big. Then, if you look at just the data for above and below the confluence of the Rio Conchos for the same time period, this is what La Junta would have experienced prior to development. Where if you were above, where I showed that picture of the gauge on the Rio Grande, you could have counted on the snowmelt pulse coming out of Colorado or New Mexico, which is the red line. And if you lived below, which is just the same place basically, you would have also experienced the monsoon peak that comes from the Rio Conchos. So this is what the system was before we developed it with Elephant Butte, etc. And then if we move forward in time to, this is 1932 to 1940, basically what we're seeing is a decline, or the width of the lines is becoming less. We still have a nice flow coming in from the Conchos. And finally today, this is what the story is now. Very little flow here, not much there. So now, this is what happens. This is what we had to deal with. I did put this star here because that's sort of a connector to something I'm going to talk about in a minute below this reach. But you can kind of make the observation yourself that we went from that in 1900 to that, whoops, well, you can see here too, but to that today. So it's the water we have to deal with. So what do we do with that? And what else is happening? For the Big Bend region, the problems that we're dealing with start with declining flows. Obviously, that's happening. There's a sediment problem. There's manipulation in tributaries. I'm aiming for there, Chonga Creek, Alameda Creek, other creeks that come in from Mexico that are delivering sediment, maybe more than they used to because of management practices. And at the same time, you don't have enough water to move that sediment. So the Rio Grande and the Big Bend is sort of choking on that sediment. And compounding that is the presence of invasive species like salt cedar and Rumidonex, the giant river king, that tend to stabilize that sediment and make it harder for the less frequent flow events that we do have to move that sediment. So here's kind of a summary of that. Dave Dean, Utah State graduate student, put together this very effective graph that I'll try to explain that shows, it's just qualitative, but it shows over time, 1900 to 2020, roughly. The upper line is channel width. He went and looked at a bunch of historic air photos and looked at how the width of the channel changed over time. And basically it kind of went up and down. until about 1940, when at the same time the relative vegetation density, which is the lower line, began to increase. That would be the Arundo and the Salt Cedar. So the presence of the sediment began to cause the channel width to decline. That's the growing problem, is the river used to be this wide open thing that flooded and stripped out the veg in the channel, and now it doesn't have enough energy to do that because there's too much sediment and too much of the vegetation. Periodically you see these little resets, like 2008 is this one, where a big flood will come in and do some good work, but it's not long before after that that decline occurs. So that's the problem, is that there's vegetation, too much sediment, not enough water. Then what we're noticing also is the segment 2306, which is Rio Grande Research Center. This is the 303D list. You're listed as impaired by even TCEQ or EPA. And we're, in our reach, we are impaired. The salinity is going up. That's told as our solid sulfate chloride. So that we are seeing that. This list of impairments does not include the part of the river outside of the immediate Big Bend Ridge. El Paso's, the list is huge. You can imagine there. The list actually increases on the Pecos, upriver and the Pecos too. But I'm focusing just on this Big Bend Ridge. But even here, we're listed due to increases in salinity. Oh, and Big Bend, this is what's happening. We're not just sitting and watching this, we're actually monitoring what's going on. But this is a vegetation removal. That's the Arundo Donax. The project that many are involved with includes going in and burning that. It's the invasive species. And then a few weeks later, they go in and spray an herbicide to try to control it. This is happening up and down the river in Boquillas and farther upriver in the national park. So these two photographs are useful for illustrating the obvious visual changes. 1936, this is the Hot Springs Tornado Creek coming into the river right near the Hot Springs of Big Bend National Park. And the same picture Jeff Bennett took from the same perspective in 2006. This is one area that's been burned and sprayed, but the vegetation is coming back. That's the Arundo Donax. What are the solutions to this? Salt cedar is another problem, and Dr. Ritzy at Sul Ross and others have worked on a beetle, which is biocontrol, which seems to be working pretty well for the salt cedar. We have a bigger problem down here with Arundo, which currently is being addressed by burning and spray. But it would be great if there was a biological control for that too. So how do we quantify that star? Remember that star on the previous slide? At the bottom of the flow maps, the river maps, I put a star because where that star is where the river benefits from groundwater flow. It's referred to hydrologically as a gaining reach. So we've done, I was not involved in this one, I wasn't young, but others have done, and I helped, seepage runs. These are synoptic studies where you go over a shorter period of time as possible and measure flow and water quality in as many places as you can during this time of the season when the changes in the amount of flow in the river can only be explained by increases in base flow, meaning from the groundwater. So you choose a time when it's not raining, where everything is static, and the only reason for a change is increases from groundwater. And so if you do that, this kind of course map shows Big Bend National Park, the sites where in one of these periods we measured discharge from basically Mariscal vicinity all the way down to Onstead Reservoir. And what you see when you do that is this graph shows river miles upstream, downstream, increases in flow, the line goes up, and what I've plotted on this graph is specific conductivity, which is a proxy for total dissolved solids. Water quality increases, the quality increases as you see that line going down. Or if I could embellish it a little bit, if the left one goes up, that's good, that's more water in the channel. If the right one goes down, that's good, that means the water quality is better. So all in all, there's a positive thing going on down there, and it's thanks to groundwater, the Edwards Trinity Plateau Aquifer specifically. I also had a graduate student, Jonas Ball, who studied just stream gauges. He didn't really go out and measure a bunch of stuff, but he mined data from USGS and IDWC. And what he found is, like on a seasonal basis, there's a increase in groundwater base flow in the winter months. So there's more base flow in January and December and less in the summers. We didn't see any huge long-term changes, but basically what he was able to conclude is, according to his numbers, is that we're gaining 226 cubic feet per second, or that's equivalent of 165,000 acre feet per year, from the aquifer into the channel of the Rio Grande. The 1944 treaty with Mexico requires them to deliver 350,000 acre feet per year. This number is not included in any of the calculations for that. So it's on top. Shared water, both sides of the river, from the aquifer on both sides of the river. It's a huge, huge increase. It's almost half of what Mexico has to deliver. Several of us, including myself and Jeff Bennett, who's in the room, were involved with this environmental flows. And what we were kind of asked to do was to look at the reach from the confluence of the Conchos, which is about here, down to Amistad Reservoir, define what we consider to be a sound ecological environment, and then determine if we had it. So we did that, and we found that everything up here, we call the Parks Reach, is not sound. It's impaired by water quality, the salinity's gone up, it's got all those Arundo-Donax problems and the sediment and all that stuff. But we said down below here, which is what we call the Lower Canyons Reach, is sound ecologically. So we made that conclusion in this, and we also pointed out that it's because of the groundwater base flow contributions from the Edwards Trinity Plateau aquifer. Another thing, as far as border relations, in 2011, then Secretary Salazar and his Mexican equivalent Elvira met at the river when they were opening the Boquillas Crossing, and all this kind of goodwill between the countries. These photos are from there, Salazar and Elvira. And part of this was to reintroduce, in this case, the river in Silvery Minnow, which was extirpated in the 60s, and to symbolically do it there. But part of that is a more reach-wide reintroduction to see if the extirpated species can survive. And that remains to be seen, because now we have Ryan Zinke, which I don't know, so I know Amy's here, she works with this, what the future of this kind of cooperative effort is going to be. Because obviously Salazar's not there, and now we have, after Salazar, Ryan Zinke. But basically the point I want to make is that this Silvery Minnow reintroduction started in 2008. It's been really a lot of effort, and a lot of effort monitoring the success of it. And if it's going to be successful, a large reason for that success is going to be the introduction of the fresh water from the Edwards Trinity aquifer, and what we like to refer to as a groundwater-dependent ecosystem. So that's my segue into groundwater, but I'm going to show you some pretty pictures first. We do a lot of work in Boquillas Canyon. This is it. And what we're doing is, with that vegetation monitoring, restoration, we're looking at, my group really, my part of it is to look at the geomorphology and determine if it's changing, if the sediment's moving. So in order to do that, we spend a lot of time with topographic surveys. This is in Boquillas at Sandbar 5. This is the USGS team, Dave Dean and Joel Sankey. This is a Regal groundwater, LiDAR system, which this thing spins around, shoots a rate of energy, and it bounces back and it makes a map. They're amazing instruments. We take that down the river. This one is a total station that I have, and this one's robotic. This is really cool. If you see the little blue circle, there's a canoe out there. Normally we use this to just do topo measurements and basic work out there. But last January we did this with a bathymetry study. So we have a prism on this canoe that's mounted on this boat that can measure depth. And so the blue instrument, being robotic, it can track it. So what you see through the screen is Todd from Utah State with our ABCP boat. And basically what we're doing is that orange boat is measuring depth and velocity, and Todd is paddling across the river. The total station that I'm looking through is automatically tracking it. So when we come back, we merge those two data sets. So we get a bathymetry map in addition to the surface map. That's pretty rewarding when that kind of thing works. If we move farther downriver, all of this, by the way, is Rio Grande Wild and Scenic, but this is federally designated as wild and scenic. You can read the details there. I'm not going to take a lot of time talking about that, but the whole reach is referred to as the wild and scenic. But in the lower canyons, when we're supporting the studies to see if the silvery minnows reintroduction is successful, and or when we're doing our own research, we measure discharge, that's Sam Birch, measuring flow. We do field chemistry. We got the whole setup to do. This is Sean and Eddie and me and Jonas. We've had really good trips with students to collect data related to this. Jeff Bennett's one of his photo points is here. This is just a descriptive kind of picture of what the lower canyons are like. Pretty important place to us. There's Upper Madison. And then finally, the Kenny Saunders from Parks and Wildlife and Diego from U.S. Fish and Wildlife sanding to determine whether or not the silvery minnows there and whatever else. It's an ecosystem sort of habitat study. And then lastly, Upper Madison. So now I'm going to make a little transition to the Pecos and pretty much just show that we have done similar work there, the synoptic gain loss studies, and pretty much the same story holds. This is the lower Pecos below I-10, where the blue line increases in width because of groundwater flow, and the conductivity, these big brown circles, get smaller, even though not as small as on the Rio Grande. The Pecos comes in typically pretty salty. This is 4,000 microsiemens up there, which translates to about 3,000 milligrams per liter. So the groundwater helps, but the Pecos is still going to be a salty river. And we have graphs to prove that we do it. I'm not going to take the time to explain all these, but basically it just says the same thing we said about the Rio Grande, is that the base flow contributions increase the flow and the water quality. I would like to point out also that I've got a student, Taylor, finishing up a similar project on the Devils. And then groundwater. So here's my switch from kind of focusing on surface water to focusing on groundwater. So groundwater is in an aquifer. Aquifer is defined as that thing that holds and transmits water. The West Texas aquifers are numerous, they're complex, they make geology at Sul Ross really entertaining because the geologic history here is just fascinating. And you've probably heard these stories about the Great Spirit dumped all the rocks out here. It makes for a complicated groundwater study. Astronauts did this, and I've benefited from discussions with Bill Mohlberger about how much fun that was, because he was their geology advisor out here, and he had a great time doing it. So instead of describing every aquifer, I'm going to give you this kind of pretty colored picture that is geologic time. And I'm just going to point out a few places where things are, and then I'm going to talk about a few of them. But if you go to Van Horn, we've got rocks over there 1.3 billion years old, somewhere in that area. And by the way, this is really old to younger, and then it goes this way. So this is the oldest, that's the youngest. Paleozoic, Mesozoic, Cenozoic, you might be familiar with. So anyway, we have rocks in Van Horn that are there. In the Marathon Basin, we have deposition all through here. And then in the Glass Mountains and the Bloods, Carlsbad Caverns, and Midland, Odessa, the Permian, oil and gas primarily is focused right in there, even though a lot of that's in there too. But you see the surface outcrops south of Marathon through there, or the Glass Mountains, or like I said, the Guadalupe Mountains National Park or Carlsbad. Geology skipped the Triassic and Jurassic out here. We don't have any deposition, but then we get a lot of Mesozoic limestone deposits that are really good. Edwards Trinity Plateau, as an example, aquifers are in this era. Volcanism started here. And then ultimately the current topography evolved from erosion of all that crazy stuff, but compounded by lots of faults and stuff related to crustal extension and the Rio Grande Rift. So the whole thing is fascinating to the geologist to try to piece together all that geologic history. And then you have to understand that to understand the groundwater and the aquifers. So what has been done is the Water Development Board, with a lot of help from various entities, have developed a system of defining major and minor aquifers. I do want to point out this is an older map. The igneous aquifer is 3 parts on this map, but the current definition is one big one. And it doesn't, there's no aquifer down here, doesn't mean there's no aquifer, it's just not in their data. And they have decided not to designate Big Bend to have an aquifer, even though it does. But in general, Jack Sharp, who will speak in a moment, and others have developed a pretty interesting regional assessment of all of this and groundwater flow paths. And we've added to it down here. We've done a lot of work that confirms this one. This is the Lower Canyons Reach where we've done a lot of work. So we can confirm that. But basically, it's a big, complicated combination of rocks from 1.3 billion years up to sediments that are related to the river today. And a whole list of aquifers, Marathon, the Captain Reef, the Edwards Trinity, the igneous and bolson models. So with funding from Water Development Board and other sources, there's been a whole series of GAMs, or groundwater availability models, developed, and they include this idea of a conceptual model. And so this one is for the Captain Reef complex. And so you have, what you do is you're building this three-dimensional flow model, so you have to understand the stratigraphy vertically and laterally. And you look at ins and outs. All these arrows are recharge or pumping or cross-formational flow to a different aquifer. And so that's what has to be built into these groundwater models so you can make predictions about how much water gets in, how much comes out, what's available. So that one's the Capitan Reef. This one is the Edwards Trinity. A little simpler, just Edwards and a couple of Cretaceous limestone layers. But yet, this one's really important. Both of them are really important because of the volume and how large it is. Edwards Trinity Plateau has that. And notice you just have to consider lots of things: pumping, evapotranspiration, recharge, various boundaries, spring discharge, on and on, in order to build those models. And then lastly, our one we exist in is the igneous and bolson GAM, and it has Cretaceous and Permian rocks at the bottom, the volcanic rocks that we live in and on here in Alpine, and then the bolson deposit, and similar ins and outs. So you just have to account for all of that. So one of the variables that we're really concerned about hitting and estimating properly is recharge. So how does water get in? We know it's 10 to 20 inches of rain depending on your elevation, but how does water get into an aquifer? Does it rain up here and infiltrates and gets in there and run off? Does it ultimately evaporate? How do you quantify that spatially on a three-dimensional groundwater model? And the way we did it in the 2004 GAM included some estimates. So I don't want to bore us too much with a complicated table, but this upper one divides the groundwater model we built for the igneous and bolson between the Salt Basin and the Pecos and the Rio Grande sub-basins, basically, like those Hut 4s and 8s I showed a while back. And we came up with, over the whole area, a percent of precipitation number. It wasn't constant across the thing because it depends on the geology and the topography. But the overall average is 1.3% of the total precipitation effectively gets into the ground to be part of our groundwater resource. So 10 to 20 inches of rain is a big area. So there's a lot of water, but it's really not that much because you really only get 1.3%. Also, to illustrate how this varies, this is a comparison. So we estimated in this, we referred to it as the runoff redistribution model. Total, these are in acre feet, I think, 67,000, whereas the previous estimate was only 30,000. A previous estimate to that was 500,000, and this is the 1% rule is 54,000, and this is the total available, that's preset. So the models in the past are really dependent on that estimate, how much recharge is coming in. And so I think our 1.3 is a pretty good number. So then if you compare that to that 10 to 20 inches of rain, it does depend on the elevation topography where you are, but it also depends on the shape, the way the water flows on the surface. And what I've put together to show that is a little game. Where is the recharge? This is a view looking south toward Van Horn. The Diablo Mountain's a big fault, salt basin right over here. So if it rains up here, what's going to happen? You know, it might infiltrate a bit. It might just run off. It might infiltrate there. There's a fault right along there. Or it might run off down here where it's just going to evaporate. It's not going to be part of the groundwater system most likely because you can see evaporite deposits. So where's the recharge? It depends on this really complicated geology. If we look at Sunny Glen, where's the recharge? So this is Alpine, we're right down here. So the Sunny Glen drainage, the Huck 12, I think it is. This is a little sub-basin defined by topography. It rains up here, it might flow down here. It's probably not going to be down here unless you may get a surface flow event that might move it here, at which point it may evaporate. But where are you going to find the most water based on recharge? Where's the recharge going to happen? Probably a lot of it's right along the front. There's likely some faults here. But it's not one number over the whole area. It depends on where you are. So it makes for a very complicated kind of model. So if we come back to this, one thing I haven't mentioned is there's springs. This is not all of them. I just stuck stars in there. But the point is there's multiple other springs that are groundwater fed. Turlinga Creek benefits. There's Duff Springs up in the upper part of Turlinga Creek, Alameda Creek. There's a ton of them in the state park, in the national park. So those feed the ecosystem. Those are also sources of water for cattle, for people. And they're all groundwater. There's no difference really. Groundwater, surface water, it's the same water. And then there's oil and gas. GSA in San Antonio, Lowell Wade gave a talk that says the Permian Basin is a world-class petroleum product. And he gave all this evidence of why. Interestingly, he thinks the Alpine High is going to be a dud. He's talking about the traditional Permian Basin, and it's world-class again because of the new techniques. He's not talking about the Alpine High. He specifically told me he thinks that's not going to be successful. That's not what I hear from anyone else, but still, oil and gas is not going away. So then if we then talk about the Alpine High, which is probably going to be mentioned a bit more later today. This is from George Vinny, who gave a talk at Midland. I think he's going to give the same talk sometime this summer, maybe at Balmer, he told me. But anyway, so there's the developed or proposed developed area. The springs that the field trip is going to tomorrow are right in there. And this is that place where that, outside of Florida, the country's deepest or longest cave or something that's under, the cave diving, amazing. George tells me, I don't know this that well, but he says the flow direction is from left to right along that recharge area and the flow path. Because then when they're doing this cave diving, they're going up gradient. The water they're going into the current because they want to kind of float back a little bit. But plus the whole system tightens up down gradient, so it's more open that way. So when they're doing the cave diving exploration, apparently it's this way, and the water's coming from the other way. And a lot of that, and this may modify a little bit over here, but a lot of that is where the oil and gas developments are. So it's a karst system. That means it's just this big wide open network of caves and conduits and stuff that they can swim through. So the point is, and the point he makes is that to the oil and gas industry is be careful. Don't contaminate that because that's going to go straight to Balmer, among other springs. And as far as I know, the plans for according to George, the development there does not include using that water. I think they're using a brine water that's deeper. So at the moment, it's not an issue of declining flows, it's a water quality. And that's a simple assessment of that. Okay, so that's it. I want to end on this. It's this big place. It's got a boundary, but it's just all the same. The same hydrogeology and surface water issues occur there as here. It's just we know more about it. And it's all a connected system. Surface and groundwater, it's all the same thing. Thank you.